Okay. Good day, everyone. So we are back at it again with only 3 topics to go. So just bear with me. I'm just trying to get my apparatus working. Okay. So we are continuing from where we last left off. So just tell me if you can see the page clearly. I'm not sure whether the camera is a bit blurry or what. Okay, that looks okay. All right. Okay. So we will move today, and apologies for the last 2 weeks. So the last 2 weeks, I could not go on with these lectures. The Saturday was... my Saturdays were packed, but we are going on from where we left off. So the last time we looked at electrostatics, and some electromagnetism, and we ended the lesson by introducing electrodynamics. Just do comment if you can see the page clearly. I'm really not sure from where I'm sitting, right? So today we'll be discussing magnetism just briefly, Faraday's law, and then we'll introduce electric circuits, right? So this will be the third last lesson that I'm taking. So I will take other 2 lessons, by which I think we would have covered the whole syllabus of physical science, right? But the physics part, not the chemistry part. So I don't have any expertise in chemistry, so I'm not going to take any chances. My expertise are with physics and mathematics, and if you notice, we've done all the chapters for grade 12 math, and now as I'm saying, we will complete all the chapters from grade 12 physics. So it's physical science without chemistry. So we go on today. We take on magnetism and we go to electricity. So what is magnetism? So magnetism, right? So it's magnetism. So what is it? Magnetism is a closely related concept to electricity, right? So electricity, it's from the movement of charges. Electric current, that is what makes electricity. Electric current is from the electrons. So it's the movement of electrons through a conductor. So that is electric current, right? And as you can hear, the word is kind of self-suggestive, like self-explanatory. Electric from electron. So that's why it is the movement of what? Electrons. Okay. And then magnetism is a closely related concept. And remember last time we said with every flow of electric current, there is an associated electric field, right? So that's what we said the last time. And now today we introduce a concept called magnetism. Magnetism is an interaction. So what is this? So this is an interaction. So it's an interaction that allows certain types of objects, magnetic objects, to exert forces on each other without physically touching each other. So these objects can exert forces on each other at a distance, right? Because if they exert forces on each other without physically touching, it means the forces are at a distance. So magnetism is that phenomena, which is an interaction that allows magnetic objects. So these are objects with an associated magnetic field, right? To exert forces to each other without physically touching. So this is like a non-contact force without physically touching. So that is magnetism. So that is the concept. And I'm sure most of us are like kind of familiar with magnetism. I mean, we know magnets, and the concept of magnetism also works with compasses for direction, and actually that is what sailors use. I think today maybe technology should have gone further than that, but initially that is how people who sail would tell which direction is north, south, east, west, because the compass, because of its orientation with its magnetic field, it always points true north. That's always the direction of the magnetic field, true north. So wherever you are, when you have a compass, its needle is pointing north. So if it's pointing north, then you can then infer which direction is south, east, or west. Okay. So as I said earlier, that the reason actually we call this concept electromagnetism, it's because it's combining two kind of ideas, the electric idea and the magnetic idea. So electromagnetism is a combination of the two. So if you have a moving charged particle, so a particle with a charge, it can be positive or negative, that particular particle has a magnetic field associated with it. So any charged particle you can think of, as much as I informed you that if you have an electron, I mean, with it is associated an electric field, and an electron is a charged particle, negatively charged particle. So it means also associated with it will be a magnetic field. So there is this kind of converse relationship between electricity and magnetism. If you have a current carrying a conductor, there will be a magnetic field associated with it, and the converse is true. If you have a magnetic field, there would be that would produce some sort of a electric field around it. So those two concepts, as I say, they are related. Okay. So as I said, that this is a familiar concept of magnetism because all objects contain charged particles, electrons in particular, if you want me to say, because all objects are made up of atoms, and atoms, the Bohr structure of an atom is that it has a nucleus in the middle, which consists of neutrons and protons, and around it is a orbiting electron. So all objects have this magnetic field because they have charged particles. But you find that maybe in most of those objects, the orientation of the magnetic field. So let's say maybe this is an object. You find that these are the magnetic field lines. Their orientation, the net effect of their orientation becomes zero because they are magnetic field lines in all directions. So that's why that maybe you find that the net magnetic field of most objects you would know is zero, because these magnetic field lines are oriented in all directions, such that the magnetic field is ultimately zero. And I think we use B, as we said in the previous lectures, for the magnetic field strength. So if it is zero, it means all those actually net up to zero. Okay. But you also have what we call ferromagnetic field. So ferromagnets. So it's ferromagnetic field. So what are ferromagnets? So these are regions. They are called domains, right? Where the electron's magnetic field line up in a particular direction. So they line up with each other to a particular direction. So they are not randomly oriented like this, where ultimately the magnetic field strength is zero. But they can be lined up in such a way, something like that. You see, this is kind of in one direction. So if you think about the net of these, it would be non-zero. It wouldn't be zero. So ferromagnets, they are objects made from these so those would be ferromagnetic objects. They are made out of ferromagnets, which have regions which are called domains, where the electrons' magnetic fields line up with each other. They line up in such a way that ultimately they are not zero, as in this case. And one example you can think of that we used to conduct when I was still in high school, we would take a ruler, rub a ruler against our skin, and kind of bring it close to pieces of paper, and those pieces of paper would be attracted to the ruler. The reason that is the case is because by rubbing the ruler against your skin, you are kind of influencing the ruler, its magnetic field, to line up in a particular direction. You understand? For such that the magnetic field becomes non-zero, right? So so that is the concept of ferromagnets. It's where you can where you can get regions which are called domains, where these electrons, their magnetic fields can line up with each other. So I think that is an important point, because you can be asked what are ferromagnets, maybe in a test or in an assessment. Right. And maybe another example you can take, maybe if you do have this old-fashioned compass, just take that compass and hold it near a wire, and just near a wire, and you should be able to see that if this wire has current, maybe it's a copper wire which has current flowing through it, but make sure this is safe, of course, and you put the compass just close enough, you should see that the needle of the compass will be deflected by which shows that relationship also between electricity and magnetism, because a compass has it's a piece of an object which has a magnetic needle within it. So that needle would be deflected, go in various directions, because there would be another magnetic field which would be associated with that current carrying wire. Okay. And perhaps an important point to make here is that the direction, the magnetic field. So let's say this is a magnetic field, and not sure whether I should have blue pen somewhere. Okay, I don't know. So and let's say you have current flowing in this in this direction. So the magnetic field, the direction of the trying to put this as some surface, some reference point from where we can say this is the direction of the magnetic field, and there is some current carrying conductor. Say this is a current carrying conductor, and the direction of the magnetic field, where there is current, where the magnetic field is induced by a current, is always perpendicular to the direction of the current. So what am I trying to say is the magnetic field produced by an electric current is always perpendicular to the direction of the current flow. So this is the relationship also between the two in terms of direction. The magnetic field is always perpendicular to the direction of the current flow, right? And how do we determine the direction of the magnetic field when we know the direction of the current? We use what we call the right-hand rule, right? Right-hand rule, and the right-hand rule simply states that if you have current flowing through a conductor, the direction of the magnetic field is given by the direction of your curly fingers, such that the thumb will be the direction. So this is the thumb, will be the direction of the current. And so if current is flowing in this direction, so the thumb will be right. You always use your right hand. You can't use your left. It won't work. And that is because of underlying physics concept called helicity, but you won't need to worry about that now. But if that is the direction of the current, and current we denote as I, or the electron flows this direction, so this is the direction of the current would be denoted by the direction of your thumb, and then your curly fingers would show you the direction of the magnetic field. So in this case, the magnetic field would be this direction, because the current is this direction. And conversely, if you are given the direction of the magnetic field, you can get the direction of the current, which should be the direction of your thumb. So in this case, you have the magnetic field pointing out of your page. If it points out of your page, if the current points out of your page, and then the magnetic field will be the direction of your curly finger. So in this case, let's consider it in this two-dimensional case. So if this is your current, and then the magnetic field will be the direction of your curly fingers, right? So that is how we think about it. So and this magnetic field, actually a guy called Faraday, actually using this concept, found a practical way of how to generate electricity. And this is what happens in power stations. This is what happens in power stations. This is how they generate electricity, by using Faraday's concept. And actually Faraday discovered that moving a magnet near a wire, if you move a magnet, if you have this is a magnet and this paper is a wire, if you move a magnet near a wire, voltage will be generated across this wire. So if this paper is my wire and this pen is my magnet, if I move my magnet across this wire, there will be a potential difference which is generated, voltage. A potential difference is also referred to as voltage. So there'll be some voltage which is created in here. And if the magnet, you were to hold the magnet stationary, no voltage will be generated. So the voltage only existed while the magnet was moving. And this voltage, is what we call the induced EMF, the electromotive force. So this produced or generated voltage, so this is called the EMF, as you move the magnet just across the wire. Why? It's because this is magnetism, and within the wire there is some